Today, we're diving into the world of complex numbers. But we're not just going to look at them as abstract algebra. Nope. We're here to uncover a hidden and frankly beautiful geometry that's going on just beneath the surface, a kind of secret language of shapes and rotations.
You know, we can all add and subtract complex numbers pretty easily, right? You just deal with the real and the imaginary parts separately, piece of cake. But what about multiplication? Sure, we can follow the rules of algebra and get an answer, but what's really happening? What does it actually look like when you multiply two of these numbers together?
Okay, so let's check this out. Let's take a complex number, say z equals 2 plus 3i. Now let's just multiply it by I. The algebra spits out -3 plus 2i. But here's the cool part. Look what happens when we plot these on the complex plane. It is a perfect 90-degree counterclockwise rotation. This right here, this is our first big clue. Multiplying complex numbers has something to do with turning.
So this brings us to our central puzzle. I mean, if multiplying by I is a clean 90-degree turn, what about multiplying by other complex numbers? How can we possibly predict the rotation and maybe the stretching that happens?
Well, it turns out the problem is the way we usually write them, that standard a+b form. It's awesome for addition and subtraction because you're just moving left and right, up and down. But for multiplication, the geometry, the beautiful rotation we just saw, it gets totally buried in a bunch of messy algebra. We need a better way to look at this.
So to solve this rotational puzzle, we're going to need a whole new perspective. We need a different way to think about where a point is on the plane.
Think about it like you're giving someone directions. You could use rectangular coordinates, right? Go 3 blocks east, then go 4 blocks north. Or you could use polar coordinates, which is way more direct. Just face that direction and walk 5 blocks. See? Both get you to the exact same spot, but the second one is all about direction and distance.
And that's the shift we're going to make. Instead of describing a complex number by how far over and how far up it is, we're going to define it by two totally different things. Its distance from the center, which we'll call r, and the angle it makes, which we'll call theta.
Now, these two pieces have some official names. The distance r is called the modulus. That's really just a fancy word for its length or its absolute value. And the angle theta is called the argument, which just tells us which way it's pointing.
So, why on earth did we go through all that trouble? Well, because with this new system, the entire mystery of multiplication just evaporates.
Okay, here's where it all clicks. To multiply two complex numbers in this new polar form, the rule is unbelievably simple. You just multiply their lengths and you add their angles. That's it. The complicated algebra just melts away.
I mean, just look at this. You have complex number A with its length and its angle alpha. And you have B with its length and its angle beta. So what's their product, C? Well, its new length is just the first two lengths multiplied together, and its new angle, it's just alpha plus beta. The rotations literally just add up. It's that clean.
This simple rule for multiplication doesn't just solve our little puzzle. It actually unlocks a kind of mathematical superpower for raising complex numbers to any power you want. And that idea leads us straight to the elegance of De Moivre's theorem.
Think about it. Raising a number to a power is just repeated multiplication, right? So to find z squared, we multiply the length by itself, that's r squared, and add the angle to itself, that's 2 theta. For z cubed, do it again. We get r cubed and 3 theta. You see the pattern emerging, right? For any power n, the new length is r to the n, and the new angle is just n times theta.
And this simple, beautiful pattern is exactly what is captured in De Moivre's theorem. It basically says that to raise a complex number to a power n, you just multiply that n into the angle. This little formula is the key to everything that comes next.
And now, for the grand finale. We're going to use this theorem to answer a question that seems really simple on the surface, but it's hiding a whole bunch of secret answers. Ask anyone what the cube root of 8 is, and they'll say 2. And yeah, they're right. But that's not the whole story, not even close. You see, in the world of complex numbers, every number has exactly n nth roots. So that means 8 should have 3 cubed roots. So where are the other 2 hiding? De Moivre's theorem gives us the formula to find all of them. And the real secret sauce here is that little plus 2 pi k part. See, adding a full 360-degree rotation, that's 2 pi radians, gets you right back to where you started. That little term lets us spin around the circle as many times as we want, uncovering all these different starting points that give us totally unique answers.
All right, let's hunt for these 3 cube roots of 8. The number 8 has a length of 8, and its angle is 0 degrees since it's sitting right on the positive real axis. So for our first root, we set k to 0. The cube root of the length 8 is 2. The angle is 0 divided by 3, which is still 0. This gives us the number 2. Okay, no surprise there. That's the one we all knew about.
But now, let's set k equal to 1. The length is still 2, but the angle is now 2 pi divided by 3, or 120 degrees. And when we run the numbers, bam, a brand new hidden complex root just appears out of the math. -1 plus I times the square root of 3.
And for the third and final root, you guessed it, we set k equal to 2. This makes our angle 4 pi over 3, or 240 degrees. We do the same process, and we find our last root, -1 minus I times the square root of 3. And there they are, all 3 of them.
And here is the truly incredible part. When we actually plot these 3 roots on the complex plane, they are not random at all. They lie perfectly on a circle with a radius of 2, and they form a perfect equilateral triangle. The algebra didn't just give us answers, it gave us perfect, beautiful symmetry.
So what this all means is that just by changing our perspective, by swapping out a plus bi for a length and an angle, we uncovered this profound truth. The abstract rules of complex numbers are actually describing a simple, predictable, and just stunningly beautiful geometry of how things turn and stretch.
We've just pulled back the curtain on this one secret world, finding a perfect geometric pattern hidden inside a simple number like 8. It really makes you wonder, doesn't it? What other mathematical secrets are out there, hiding in plain sight, just waiting for us to find the right way to look at them?